So, what have we done in the book so far? We started with average rates of change. The average rate of change of one function with respect to a variable. Then in the second section, we talked about the prelude to instantaneous rates of change. We talked about how you would go from a notion of the average rate of change to a notion of the instantaneous rate of change. So from like average velocity between 2 times to what is your instantaneous velocity at time, pick some number, time 2 seconds. And we decided you need to take very, very small changes in time and look at your average velocity there and take a limit as that change in time approaches 0. And for a general function, the instantaneous rate of change of the function with respect to the variable, you take a limit of the average rates of change as the change in the variable approaches 0. We did that in an informal way, and then we had the notion of limits, and we discussed limits and continuity in section 3. In section 4, now that we, after having developed the rigorous notion of limit, we could give a rigorous definition of the derivative, the instantaneous rate of change of a function with respect to a variable. We developed a few rules, like the derivative of a constant times a function. You can just pull the constant out. The derivative of the sum of 2 functions, you can split up into the sum of 2 easier derivatives. We found that the derivative of the constant function was 0. The derivative of x is just 1. The derivative of x squared is 2x. There's a small obstacle, well, not a small obstacle, there's an obstacle for us in looking at many interesting examples right now, because we need to develop more rules for calculating derivatives, because right now, every time we do an example, we spend most of our time doing algebra and working out the derivative from the definition. And in the next chapter, we'll eliminate that difficulty by developing a whole set of rules that will enable us to differentiate essentially anything we see. Almost anything we see. The normal functions that one sees, the elementary functions. But before we get to the rules, there's one more topic that I'd like to go over, and that's higher order derivatives. So what are higher order derivatives? Probably the fundamental motivating function for defining the derivative was position as a function of time and warning velocity. So suppose we've got the position of an object as a function of time. So this is the position in meters of an object, some object, a particle, a car, of an object at time t seconds. Right. Then, as we discussed in the first section on average rates of change, and in the section on prelude to instantaneous rates of change, and in the last section, the velocity, well, the average velocity is the average rate of change of the position with respect to time. But the instantaneous velocity, your velocity at any point in time, is the derivative of the position with respect to time. It's p prime of t, so this would be your velocity. We also discussed acceleration. Acceleration is the derivative of your velocity with respect to time. So acceleration equals v prime of t, the derivative of the velocity with respect to time. Acceleration and velocity are things we experience every day, and most people have a feel for these things. If you think about this, and you don't have to think very long, it means what's acceleration? The acceleration then is we took the derivative of the position, and that gave us the velocity, and then we took the derivative of that. So the acceleration is the derivative of the position with respect to time, where even the first derivative was with respect to time. Both derivatives that I used in that sentence were with respect to time. this process of iterating derivatives with respect to the same variable, so with respect to t and with respect to t, comes up often enough in enough applications that we want to develop terminology and notation for it, even in situations where we don't have names like velocity and acceleration. So we make a definition. So suppose you've got just an arbitrary function. Of course, I'm going to say something about the function's derivatives, so we need for it to be differentiable somewhere, or what I'm saying doesn't have much meaning. Suppose that y is some function of x, or it's like p equals a function of t. You could use any variables, any function names. I'm just using the standard ones. Suppose we've got y as a function of x. The second derivative of f with respect to x is the derivative of the derivative. So you take p prime of x, so f prime of x. So you take the derivative of f with respect to x, and then you take another derivative of that with respect to x. The notation for that, we usually put the two primes right here and read this f double prime of x. F double prime of x, the second derivative of f with respect to x. It also has other notations. We can use the Leibniz notation with the d's in it, where things look kind of like fractions. I remind you, they're not actually fractions, but they look like fractions. In that notation, we would write the second derivative of y with respect to x like this. The 2's go there and there. That may look a little strange, but I'll explain that in a second. Or if you just have it in terms of f, second derivative of f with respect to x, or if you might write f of x over here in parentheses. All of these notations mean the same thing. They mean the derivative of the derivative, both times with respect to the same variable, x. All right, why is this notation like this? Why are the 2's where they are instead of like both over here or both over there? It's because we're thinking of applying the differential operator d dx twice. So it's if you do d dx to f of x. Right, that's the first derivative of f with respect to x. And then you would take the derivative with respect to x of the derivative with respect to x. And so it looks like d dx is multiplied twice. It's not multiplying, it's performing this operation, derivative with respect to x. But just notationally, we act like we should use similar notation to multiplying. So it's as though this were squared. So it's more like this. And then we just put this here, and yeah, it doesn't really look like the quantity dx is squared, but that's what you're supposed to think, that it's like that fraction and we squared it. So anyway, that is the notation for it, whether you like it or not. It's classic. It's not going to change. This is what you get. All right, or this is what you write. There's no reason to stop at the second derivative. It's depending on the problem, there might be no physical significance that to you or to the problem you're dealing with of many higher derivatives, like the third derivative, the fourth derivative, but there's certainly no problem defining them. By the way, all of these are called higher order derivatives. Derivatives beyond the first derivative are referred to as higher order derivatives. So what's the nth derivative? The nth derivative of f with respect to x. It's the derivative of the n minus first derivative. So is the derivative with respect to x of the n minus first derivative. What do I mean by that? So, for instance, I mean the third derivative is the derivative with respect to x of the second derivative. So, d dx, derivative with respect to x of the second derivative of f with respect to x. This would be the third derivative. What would be the notation for it? It looks like you've cubed the differentiation operator. So you would put 3's here. The notation with the primes, you don't want to write n primes, like the fifth derivative. Yeah, for the fifth derivative, you could just write the fifth derivative of f with respect to x. Fine. How do you write this in the primes? You don't really want to write 5 primes and, or 17 primes. Not that I can think of a physical significance for the 17th derivative, but still. It has mathematical uses that you'll see when you get to infinite series. But how do you write this in the prime notation? Actually, we typically drop the prime notation after maybe the third derivative. So for the third derivative, you might write f triple prime of x. But for the fifth derivative, you would not write that. You would write f, and then you put the number of derivatives in parentheses. So the parentheses are important. It tells you that you're taking the nth derivative, instead of possibly raising to the nth power. So this is our notation for the nth derivative. It's this fnx, or right. What are the units? What are the units on these higher derivatives? This should not be this should not be a confusing question for you. You should kind of know, or you have the knowledge to figure this out yourself. When we have position as a function of time in meters and seconds, fine, we know the derivative. We know the units on the derivative. Units on the derivative are always the units of the function divided by the units of the variable. So, for instance, the units on velocity, the units of the position function, meters, divided by the units of the variable, seconds. So this comes out in meters per second. The units on the acceleration, it's the derivative of velocity with respect to time. So you take the units of the velocity function, meters per second, and you divide by, so that's the units of the velocity function, but you have to divide by the units of the variable again, meters per second per second. And while I've said that I don't really like doing algebra with units, I will this time. It's meters per second squared. If you keep iterating derivatives, all that happens is you keep taking more derivatives with respect to time. You keep dividing by more time units. And so what are the units on the nth derivative? It's the units of f divided by the units of x raised to the nth power. So maybe it would be best to do this first in terms of position and time, and then write in general what happens. If you took the nth derivative of position with respect to time, still with position in meters and time in seconds, the units as units of meters per second to the nth power. So when n is 2, yeah, of course you get meters per second squared for the units on the acceleration. And the same thing with y and x, the units here, the units of n of x would be, or the units of f divided by the units of x raised to the nth power. All right. One last comment on this notation and terminology. Every now and then it might be useful for us to talk about the nth derivative even in the case when n is 0. I said you do this for positive integers n, but when n is 0, what should the 0th derivative of f mean? Well, you haven't taken any derivatives. It means f itself. So if we ever use that, that's what it will mean. The 0th derivative of f with respect to x is just f of x. Back again. All right, that's the notation and terminology for the higher derivatives and the units. This is the short section. What I want to do now is talk about 1/3 derivative that you actually experience in real life, and then look at second derivatives graphically and do one velocity and acceleration problem, and then leave any harder problems or more interesting problems until we have some more rules for calculating derivatives. So what is a third derivative that you experience in real life? All right. Let's recall Newton's second law of motion. For an object with a constant mass. This is the usual case, but certainly if the mass changes, this is not all that you need for an object with constant mass. Then Newton's second law in this case is the very familiar, the net force acting on an object. I'll just write F for the net force. The net force acting on the object is the mass of the object times its acceleration. F equals ma, rolls off the tongue. The net force. And this is the acceleration of the object. Okay. What is it? So suppose you're in a car and you're accelerating at a constant rate. Then you feel this force pressing you against the seat. And if you're accelerating at a constant rate, that force will be constant, so you feel this constant force acting on you. But then when the acceleration changes, suddenly you'll jerk forward or backwards into the seat. If there's suddenly a lot more acceleration, you'll jerk backwards. If suddenly there's a lot of deceleration, you'll jerk forward. Why do you feel that jerk? Because the force on you changed. And so what you're feeling is the rate of change of the force acting on you with respect to time. This when you feel a jerk. So. You're feeling that the force is changing. So you're feeling this rate of change of the force. Right? If the force were constant, so we know the derivative of a constant is 0, you wouldn't feel a jerk. You just feel this constant pressing. But when you feel a jerk, you're feeling df dt. But df dt is the derivative of this, and this is a constant times the acceleration. We know we have a rule for that. The derivative of a constant times a function of t. You just pull the constant out and multiply times the derivative with respect to t, the other thing. So when you feel a jerk, you're feeling df dt, or since m is constant, that's df dt is proportional to dA dt. So you could equally well say that what you're feeling is the rate of change of the acceleration. So we give the rate of change of the acceleration a name, and we call it jerk. So it's not something that gets talked about too often, but it is a third derivative that you experience in real life. Definition, the jerk, or the jerk. It's the derivative of the acceleration with respect to time. This means that it is the third derivative of position with respect to time, because it's the derivative of the second derivative of the position. So it is the third derivative of p with respect to t. And it's one that you do experience in your day-to-day life. So these higher order derivatives do come up. They do have physical significance. It just depends on your setting. All right. Can you see these higher order derivatives graphically? Well, you can certainly see the second derivative. And we will come back to this later in the book when we do an entire section on what derivatives have to do with graphing. But we can look at it right now. Suppose we have the graph of some, well, it's a cubic polynomial, but I don't want to actually calculate derivatives of something cubed until we have some more rules. But the graph of a cubic polynomial looks roughly, could look like this. So suppose we have a graph that looks like this. Can you see the second derivative in this graph? Maybe. How do you see it? Well, so suppose we start with, suppose this is the graph of y equals f of x. Graphically, the first derivative is the slope of the tangent line. So f prime of x equals the slope of the tangent line at the given x coordinate. But the second derivative is the rate of change of that. So the second derivative, f prime of x, equals the rate of change with respect to x, so instantaneous rate of change with respect to x of the slopes of the tangent lines. All right. Can you see that on a graph? Well, we can see whether it's positive or negative on a graph pretty easily. So let's take this graph. I'm going to draw in some tangent lines. And then we're going to look at how their slopes are changing. And we should be able to see where f double prime of x is positive and where it's negative. Positive should mean the rate of change, okay, that would mean the rate of change of the slopes is positive. That should mean the slopes are going up. So they're increasing. F double prime being negative should mean the rate of change with respect to x of the slopes is negative. So the rate of change is negative. That should mean that the slopes are going down, so that the slope should be decreasing. So let's look at it. I'll sketch in little pieces of tangent lines. So there's one. Maybe I'll switch colors so that you can tell more easily where they are without bumping into things. Let's try yellow. So I'm sketching in a whole bunch of pieces of tangent lines. All right, well, let me move to a more interesting point. All right, so what happens? You've got, here's some tangent line. It has a large positive slope. And then you move a little bit, and this tangent line has less positive slope, and then less slope, and no slope, zero slope. So very positive, less positive. The slopes of the tangent lines are decreasing. So the rate of change of the slopes of the tangent lines is negative. So yeah, that's what you see here. But what does that mean you're seeing? You're seeing this graph curve downward, exactly because the slopes of the tangent lines are doing this. Boop, 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 boop. So that you're curving downward, and you see the graph curving downward. We call that concave down. We say the graph is concave down there. And what you're seeing when you see that is that the second derivative is negative. The rate of change of the slopes of the tangent lines is negative. Then it continues to be negative because maybe this slope looks like it's about 0, but then you come here and this slope is negative. So you continue to decrease. The slope continues to decrease, so you keep seeing something concave down, kind of cupped downward. Some people say that if you dropped water on this, it would roll off, and where the graph is concave up, if you dropped water, it would be caught. Yeah, whatever. Anyway, so the slope continues to decrease, but then it's more negative here and then less negative here. So the slope is still negative here, but it's not as negative as that was. So the slope increased between here and here. And then as you go over here, the slope actually becomes positive. It was 0 around there. I don't want to draw in too many lines or we won't be able to see anything. But the slope continues to increase over here. So it started increasing. The slope is getting bigger. Negative, 0, positive, more positive. And that goes well with our intuition that we developed over there. That's concave down. And that what we're seeing is that the slopes are decreasing. Over here, this became concave up. And that's a sign that the second derivative is positive. Again, we will do this in detail later in the book. Concave up, f double prime, should be greater than 0. And then there is the point where they switched, where the graph switched from being concave down to concave up. It looks like it's about there, right, where it stops curving downward, or maybe it's right on the y-axis. In any case, there's this point where the graph switches from curving downward to curving upward. That, where the concavity changes, I'll just go ahead and say the word, that is called an inflection point. All right. So the point of this is that you can see second derivatives graphically. Third derivatives, yeah, you can't really see those in the graph. Qualitatively, yes, if you knew the graph in enough detail, of course, you could decide exactly what the function f was, so you could figure out any of the derivatives. But I mean, just looking at it, looking at the qualitative nature of the graph, yeah, you see slopes of tangent lines, you can see the rate of change of the slopes of the tangent lines, so you can see first and second derivatives in the graph. Seeing derivatives beyond the second one in the graph, difficult to do just by eyeballing it. All right, let's calculate one example, and then we'll go on next time and develop rules that will enable us to do more complicated, more interesting examples. So, suppose just an example. In fact, this won't look new because I'm just going to use position as a function of time. suppose I'll use our new notation and I'll calculate the jerk also, so that part will be new, but basically this will just look like stuff we've been doing. Suppose that P of t equals, let's see, there was a specific 5t squared minus 2t minus 1 meters. So, suppose that the position of an object is P of t equals 5t squared minus 2t minus 1 meters at time t seconds. All right, I want to find the first, second, and third derivatives of this. The graph, you should know what the graph of this looks like. This is a quadratic polynomial. It's got a positive coefficient here, so the graph is a parabola that curves upward. You could figure out the t-intercepts using the quadratic formula. We only really care about the qualitative nature of the graph. We can figure out those things. So let's see, when t is 0, we're at minus 1. So something like this. Okay, well, maybe I'll make it look more parabolic. Okay, so the graph is a parabola that curves upward. Great. So what's p prime of t, the velocity? All right, the velocity. We actually have rules that tell us how to calculate this. We looked at it, this kind of thing last time. We've got a sum of three things, or a sum if you think of adding the negative this and adding negative 1, or you can think of it as a difference. Either way, we know that from last time, we know you can split up sums and differences when taking derivatives and pull out constants. So what I mean is that the derivative of this is 5 times whatever the derivative of t squared is, minus 2 times the derivative of t, and then there's minus the derivative of 1. Right? You can just split up sums and differences, look at those as different pieces, and take the derivatives of the individual things. So the derivative of 5t squared, but you can pull constants out of differentiation. You just get the constant multiplied times the derivative. And we know the derivative of the squaring function and the identity function, so just t. We talked about it when it was x. The derivative of f of x equals x is just the function that's always 1. Same thing if it's the function f of t equals t. It doesn't matter. So the derivative here, 5 times 2t minus 2 times the derivative of t is just 1. The derivative of constant, 0. So we get 10t minus 2. The units are important, meters per second. Great. That's p prime of t. The acceleration is p double prime of t, the derivative of the position. And we can calculate that easily with our rules. So what do you get? Acceleration, which is the derivative of the velocity, which we now also write as the second derivative of the position with respect to time, is the derivative of the derivative. So it is the derivative of 10t minus 2. Again, you split up sums and differences, you pull out constants, you get 10 times the derivative of t minus the derivative of 2. The derivative of t, it's still just 1. Derivative of 2, that's a constant. It's 0, so this is 10 meters per second per second. I guess I will write meters per second squared, but really physically meters per second per second. Notice that this is positive. It's positive and a constant. We saw just a few minutes ago, or just a couple of minutes ago in the other graph, this graph is concave up everywhere. Concave up should mean a positive second derivative. Well, our second derivative is positive. In fact, it's a positive constant, but it's certainly positive. That's meters per second squared. And finally, we can calculate the jerk. I guess I'll write a J for jerk. This is the derivative of the acceleration with respect to time. That is the third derivative of position with respect to time. It's the derivative of this 10. It's 0. 0 what? Meters per second cubed. Right. There is no jerk. If you were moving at this rate, you would feel no jerking motion whatsoever. All right, well, we will continue to use higher order derivatives throughout the course. This is an introduction to the notation and the terminology. We will use them more extensively when we have rules at our disposal that will enable us to deal with more complicated functions and more interesting examples. So next time, we'll start developing rules for differentiation.